In the previous presentation, we defined a simple grammatical model, or rather a scheme for a grammatical model, in which we start from a set of primitive elements, let's say words, and then we go through all possible ways of assembling complex expressions from those elements. So we go in some well-defined order, every possible way made available by our grammar or theory of deriving sentences from that starting point. And the assembly operation and other similar processes that are defined by our theory or hypothesis will create hierarchical representations of some type, which are then linearized into concrete sentences that we will have in the dataset that we see in the observed reality. So that's the basic idea. Now notice how ultimately this type of model will define a set of expressions. For example, a set of attested sentences by simply listing them. So we can start from, for example, from a set of words, and the grammatical model will then provide us a list of expressions which it predicts to be attested, part of observed reality. So it's a defining a set of attested expressions or meanings, ultimately. But this is just one way of defining the set. There's an alternative which will be the topic of this presentation. I will, for the sake of completeness, simply mention this alternative here, describe some of its properties, but without going much into the technical details. This is because the next presentations we will focus on the first model. It's more simple to understand and to define and implement. And then only in the later presentations I will return to this alternative model in some more detail. After I've provided simple definitions for these notions and clarify some of their properties, I will then conclude with some random comments in no particular order. But the main topic will be simply to acknowledge that this type of membership enumeration is not the only way of defining these sets. But let's first make some observations about the first simple model. In all examples I've discussed so far, we have started from a set of primitive elements like words. But in a more realistic project, we can't assume that the dataset contains, that every sentence in the dataset is based on the same primitive elements. So in more realistic approach, the dataset will have to have a list of primitive elements, a list of sets of primitive elements, each corresponding to a sentence or expression or a class of expressions in the dataset, depending on the words or morphemes or elements that appear in those expressions or elements which are required to derive them in our theory or grammar. And ultimately, in a more ambitious model, we could begin from a complete lexicon. A lexicon is simply a list of words. In this case, it would be a list of words or items or elements that appear in the expressions in our data set. And then the model would create all possible permutations of those elements. I mean, all possible subsets that you can create from that list, together with some examples where we have repetitions. Expressions like John likes John, for example. And then all these permutations will be fed to the model in a well-defined order. But in each case, the set of expressions is defined by listing or enumerating its members. And I will call this type of models enumerative grammars or hypotheses, theories based on enumeration or enumerative grammar. So when I'm using this term, we have to think about a model which enumerates or lists all attested grammatical expressions from a set of primitive elements by going through all the possible assembly processes. Now there is an alternative way of defining the same set or set of attested expressions. And that is that instead of listing its members, we could create a model which looks at all possible inputs. Let's say that we are looking at surface sentences, linear lists of words. And then for each possible input sentence, the model will decide whether it belongs to that set or not. So it sort of recognizes whether a sentence is grammatical or ungrammatical. For example, if we are interested in grammaticality. And so it doesn't have to generate itself. It doesn't have to list the members of that set. It will just recognize or assess the properties of each individual item. But it can define the same set. There are just two different ways of defining set. Listing the members, or we can decide from any arbitrary item if it belongs to the set or not. This type of algorithms or models are usually set to implement the characteristic function for the set. And so, because both of these models can define sets of expressions, we can create a hypothesis or theory of grammar that is based on recognition and not enumeration. Just to define another term, traditionally the term generative grammar referred to a grammar or explicit grammar theory or hypothesis which defines sets of expressions. And so on such basis, we can have two types of generative grammars. One that is enumerative grammar, which is literally generating the members of that set one by one in some well-defined order. And another is a recognition grammar, which provides its characteristic function. So both enumerative and recognition grammars are generative grammars in the technical sense of the term generative grammar. This was the sense that was originally used in the 50s and still in the 60s. Then the term acquired additional meaning, which is something that I perhaps comment at the end of this presentation. But here, in these lectures, I will be using the term generative grammar in this more technical sense. So those are the two ways. And now, because they can be used to define the same set of expressions. They are, in a mathematical or formal sense, equivalent. They do the same thing. Deep down, these ways are the same. They do the same thing. There are some situations when we don't have this equivalence. For example, if we define a grammar that will recognition grammar that will never produce an output for some expression. So then the question of equivalence is non-trivial, but this is something we will never consider here. So we can just treat these two ways as equivalent to each other formally, in a formal or mathematical sense. Now there is a way to understand this equivalence. Imagine you have an enumerative grammar which from a list of primitive elements it creates provides a list of members of the set. We can always wrap this enumerative procedure inside a recognition grammar by creating a simple function which takes the input expression, let's say just a linear sequence of words, and then it breaks it apart into its elementary elements like words, and then it goes to the derivational mode and creates the set of attested expressions one by one, and simply checks if the input expression is in that set or not. So here we have a enumerative grammar that has been wrapped inside of a trivial layer which transforms it into a recognition grammar. But the underlying model, the empirical model or the empirical assumptions here are provided by the derivational grammar, because the recognition layer is simply a trivial layer that does this matching. That's important to keep in mind. We can also do vice versa. Suppose we have a recognition grammar that provides a characteristic function for the set of expressions. We can trivially transform this into an enumerative grammar by creating a function which produces all possible combinations of the input elements or morphemes. Again, remember, we can talk about set of expressions or set of expressions or even a whole lexicon. That doesn't matter. We just have a function which provides this model, this recognition grammar, every possible input that can be permutations of those input elements that we are focusing on. And then we use the recognition grammar simply to recognize those input elements, whether they are members of the set or not. And so the output will be a well-defined order of expressions listed that define the set. But again, in this example, the real principles, the empirical content of the theory would be inside of the recognition grammar, and the enumeration will be simply a mechanical system which produces all possible inputs in some well-defined order and then applies the characteristic function for every one of those. And then the result is a listing of expressions. So in this way, these two approaches are equivalent. But as empirical theories or starting points, they are not equivalent. And also the way how the data is handled differs. For example, if we consider a data set that has only one expression, let's assume that we have a grammatical attested expression in our data set. In an enumerative grammar, we will break that sentence down into its primitive constituents, primitive units like words. And then we start the enumeration. We go through all possible derivations. And let's assume that the output output set contains that one sentence expression. What happens here is that we make up the model makes a prediction that indeed that one expression is attested. But it will also predict that every other way of deriving sentences from those primitive elements is unattested. Why? Because it was not able to generate anything else. So everything else that could in principle be derived from those words was, and in this case was correctly judged unattested or ungrammatical. In other words, enumerative grammar, when it provides you the list of elements in the set, these members, it will always implicitly say that everything else that could be derived from these items or even from the whole lexicon is predicted to be unattested. But if you look at the recognition grammar, let's say that we apply this characteristic function for that one expression. And let's assume that it will correctly recognize that the sentence is grammatical or attested. So the model is in that sense correct. But because it's a recognition grammar, it doesn't tell us anything about any other permutations of those elements. It will just classify that one item. And in order to verify that no other combination of those morphemes, say, will be wrongly just as attested, we will have to test the model explicitly by feeding it with all those input expressions. So you can see that there is a difference in how they handle data. The enumerative grammar does more work because it is trying all possible derivations, but it's providing us also more information when it's completed. The recognition grammar has to be tested with explicitly with more expressions. And finally, I want to make a comment that explain why they could be and often are different from the empirical point of view, different approaches. The first point to see this is that intuitively at least, the recognition grammar corresponds to language comprehension. It's obvious that our brains implement some type of characteristic function because we really, when you put participants into laboratory experiments and show them linguistic stimuli, they will be recognizing their properties and classifying them. A procedure where we would take some words and we would be asked to produce all possible grammatical sentences from those words is a different type of thing entirely. It's a kind of artificial task. Whereas one could start from the assumption that language production begins by assembling some type of, let's say, motoric plan from the primitive parts, rather than recognizing anything. And then if we take this perspective seriously, so I'm not claiming that that's a good starting point at all, and that's not, we don't have to start from that assumption. We don't need to think that comprehension is recognition and enumeration is production, not at all. But if we take that idea seriously, it's then easy to see that if we think about things like phonological null elements, just to mention one example, elliptic structures, missing pronouns, or any type of linguistic elements that we might consider being part of the linguistic processing but doesn't have any phonological exponent in the surface expressions, then the recognition grammar will have additional question, let's say problem or challenge, what will it do with that type of elements? Because they are invisible, they are not in the input expressions. Whereas in the enumerative grammar, we can really insert those elements into the into the sets from which all these derivations and assembly processes begin. It doesn't matter if there is a word that doesn't have phonological exponent. It's just one part of the items that are combined, and then only in the final stage when we produce linearization, that element will just produce silence because it doesn't have phonological exponent. So there's no problem. But in the recognition grammar, that creates an additional challenge. Just to mention one example. Now, why recognition is not necessary comprehension and enumeration is not necessary production? Simply because we could produce sentences in a real, I mean talking about the real-time, real language production. We don't have to produce them by starting some set of primitive words and then trying to create complex plans, motoric plans, or semantic representations from those words. We could also generate them by simply going through from left to right, one word at a time. We just plan the next word and the next word and the next word. And then this recognition algorithm would simply work there in the background implicitly. For example, it could check that how we are sequencing these words produces the intended meanings, for example. Or we could use enumerative model in language comprehension if we assume that when we are comprehending words, at least in some cases, what we would be doing is taking some elements and trying to assemble them into hierarchical units. It's not impossible, or perhaps it's not even implausible that something like this that could happen. And then we could have models which combine both, and both in connection between comprehension and production. So that's the basic point. We are trying to construct generative grammars in the technical sense, and we have two ways of approaching this problem. We can use enumeration and enumerative grammars, and recognition and recognition grammars, the latter which will provide a characteristic function, and the former which will simply list the members of the set. These are mathematically equivalent for our purposes, so in that sense it doesn't matter what we use, but the choice will have some effects on the empirical assumptions we make, the nature of the grammatical rules that we will end up proposing. And in the subsequent presentations, I will develop the enumerative grammar model first, and then return to the recognition grammar later. And so now I will conclude with a couple of comments. One comment is about, well, first of all, first comment I have here is that the term computational generative grammar. The computational generative grammar is a linguistic theory or hypothesis that is justified against the dataset, and here by using the methodological principle, either by enumeration, namely by listing all the members of the set, this data set, or by recognition, by providing a characteristic function for that set. I'm assuming, of course, here now that the data set defined by the theory, the grammar, is checked against the data set, the observed facts. It's implicitly also presupposed in this definition. So the computational refers to the fact that we will have to use computational techniques to actually implement this, as I discussed in previous presentation. And the generative grammar refers to the generative grammar in the technical sense. We are trying to define a set of expressions, meanings, or pragmatic context, or whatever it might be. So that's the first point. Then the second point, I wanted to make a comment about the term generative grammar itself. And the reason this requires a comment is because in the technical sense, the term was first in the 50s defined in the sense that I just provide. It's an explicit grammar or unambiguous grammar which defines a set of expressions. But then over the years, when other researchers began to develop these ideas further from the 60s onwards, this term has acquired another meaning. It no longer, and this is the meaning that it's used today, but also the meaning that I won't be using it in these presentations. First, the generative grammars, more modern generative grammar theories, let's say, they are not generative grammars in the technical sense. I will be using it here because they're not unambiguous and they don't define sets of expressions. And they don't define sets of expressions that would be compared with the data sets. That's the first difference. And the second difference is that they also make more substantial empirical assumptions about human linguistic behavior and languages. So we have different approaches like minimalist grammar, principles and parameters model, government and binding theory. Then we had extended standard theory, aspects model, and others. Now these are all said to be specific models developed inside this more broader umbrella of generative grammars. But here notice that they make more, these models differ from each other, or approaches rather, in the sense that they make different assumptions concerning the human language. Empirical assumptions. That's what defines their content. And they are also not generative grammar models in the sense that none of those define sets of expressions that could be checked against data sets, or that we could apply, that have been justified by using the scientific method, the methodological principle I discussed in the second presentation. So they are completely different thing. And I don't want us to confuse the term generative grammar with those specific but non-generative grammar. Not technically, they are not generative grammars. I don't want to confuse the term with them here. Now, what are those models really? Apart from the fact that they make empirical hypotheses about human language. What is the underlying principle there, methodologically, if they don't use the scientific method? So this is my interpretation, what's happening. The fundamental assumption seems to be that the hypotheses or theories are justified by data on the basis that we believe, or the author believes, that the data follows from the hypothesis or theory. So what you find from the primary scientific literature are sketches of arguments, or let me say that different, that's not correct. They are sketches of proofs, which are then part of the argument. And so what is required, because we don't have the actual proofs, we don't have unambiguous theories, unambiguous data sets, or unambiguous connections between those. What you are asked to assume then is that you are asked to believe that that type of justification or rigorous demonstration exists. But you are never shown what it is. So that, to me, looks to be the underlying methodological framework. It looks like when you read the primary literature that the authors are, they are sketching or storyboarding the proofs. They are showing that here are a couple of examples, and then they sketch some kind of phrase structure images, or sketch some kind of operations, merge and agree and move. They are just pseudo-formalistic. Sometimes they are not even formalized, but there are some type of pseudo-formalistic definitions are provided. This could be the starting point for a more rigorous model, but I'm not going to go there. I'm just going to sketch that this is what I'm sketching. I'm sketching that this could be a good starting point, and then I will show that for some expressions I'm interested in at the moment, the correct set could get defined. Correct distinctions, correct meanings, and so on and so forth. But there is never a complete data set. It's maybe too strong to say never, but let's say in most cases, or in the overwhelming majority of cases, there is no data set, closed data set, that we would know, okay, that these are the data points that we are interested in, or we will demand that our hypothesis explains. We have a kind of few scattered patterns or expressions. And then we sketch the ways how they might come out from our hypothesis. So really I feel that what's required here is that the author is claiming that he or she believes that a real proof is possible from these empirical assumptions. I might be wrong, but that's the impression I get. And then the argumentation proceeds so that another person, another researcher comes to show that there seems to be a problem, as some expressions are not calculated correctly. We don't see the demonstrations, but we are asked to believe that there could be a problem. And then another model is presented for which a similar sketch is provided. So we can say then that this literature, it contains arguments, that this is a type of argument for a particular model, because we are suspecting that the old model is wrong, and then we suspect that the new model is correct or better, and we provide some reasons to believe that that could be the case. So it's an argument, but not justification. It's a tentative argument. Then sometimes in some articles, especially those which are much longer, the material seems to be composed of the discovery process. So it carries a long argument which mimics or seems to follow the logic of discovery. So you notice there's a problem and you develop a solution. Then you get some examples that you believe support your solution, and then you start going through possible alternatives. So that's a discovery process where you rule out hypotheses one by one, and you're left with one, and then you sketch what that hypothesis will be. And that's the end of the story. But in a scientific method, all of this process is completely hidden, or it's never reported. Because after the discovery process is over and you have sketched all of this and you have ruled out ideas and you are left with some idea, then the real work begins, where you compose the data set and you formalize and make your hypothesis completely unambiguous. And then you start the checking process, and then you would report that. You don't need to report these informal steps where you ruled out something else as implausible. If you want to, but this never happened in real science, so it's difficult to imagine, but you could in theory also formalize a hypothesis that you reject. And then after you have formalized it, you could show that the dataset, it doesn't calculate the dataset. But that's not so relevant, because in a normal science, every publication, every piece that is in scientific literature reports something that satisfies the sufficiency condition. So that's kind of trivial requirement. So you don't have models which fail. They are never reported, and you never need to consider those. So that's why it feels irrelevant. Okay, and then another comment still, that what I'm saying is not misunderstood. It's that I'm not claiming that the discovery process is irrelevant. I'm not claiming that it's unimportant. I'm not claiming that it's not worth reporting. It's not reported in a scientific literature, but it's something that is interesting, and it's part of history of science and sociology of science and other things which are not irrelevant. And the discovery process is something that is part of the education, scientific education, and the way how you teach it is important. So that's not what I'm saying. Also, I believe myself that the discovery process is the secret to progress in science, and it's the method that we really reach results. We find truths which the field as a whole can eventually accept. I also believe that the discovery is based on human intuitions and personality characteristics, personality, preferences, background assumptions, and that those things are extremely important when we think about scientific progress. Maybe they are much more important than the justification itself. So by no means this means that we should eliminate them or criticize those things. But what I'm saying is that the discovery process, whatever its value is not the justification. That the scientific method requires that we demonstrate that the data follows ultimately that the data follows from our idea. So that's the basic reason why I ignore generative grammar in that sense here. it doesn't use the scientific method, proper scientific method. So it's difficult to evaluate even. The theories are difficult to evaluate because we don't know what the theories mean, they are ambiguous, and there is never data sets, and there is never any real demonstrations. And so even though they make different assumptions about the human language and human linguistic processing and behavior, and even though some of these ideas might be true and relevant, as I believe some of them are, we don't know that yet because we haven't really formalized those ideas in a rigorous context, and we haven't checked them against systematic large data sets.